is if you look at, let me get this out, we can look at this code. All right, so this is kind of like mimicking hitting an API, right? So you can imagine like we hit the Foursquare API and then we hit the Spotify API. And you can see what's really happening is it's like, all right, I'm about to call the Foursquare API, and then we just sleep for 2 seconds, and then we finally say, okay, we're done. And now it's like we're about to call the Spotify API, and then we sleep for a second, and then we say we're done. So if you think about like how long it's going to take for these requests to occur, this is going to take us 2 seconds, and then when this is done, right, 2 seconds, and then when this call is done, then this will start, and so this will take us now like 1 second, you know. So we can run this and just see. So Python 3 index.py. So right, we're waiting our 2 seconds, started, finished, and then this guy started, and then it finished. So just notice again, right, started, wait 2 seconds. Now right away we go to this one, start, and then it's done a second later. Now, if we move to like the asynchronous style, which you don't have to understand this code right now, I just want you to see the benefit. If we move to the asynchronous style, which is in sample.py, this should actually only take us, we sleep again. It should basically only take us 2 seconds total instead of 3. So see that? Right away, let's do it one more time. Right away, it's going to go Foursquare call and then Spotify call. Okay, so let's see it again. See that? Foursquare and Spotify right away. So that is the key benefit of asynchronous programming. Normally what's happening is let me share my screen. Nope, not that. Let's share the whiteboard. Okay, so normally what's happening is you have a thread, and it's like, we have like call the Foursquare API, so call Foursquare, and then it's going to wait 2 seconds, and then it calls Spotify. Okay? But instead, so this is the sync programming, or like the normal. Okay? And then with async, what happens is it's going to call Foursquare and then call Spotify right away. So it's like I'm going to kick off the Foursquare job and kick off the Spotify, like kick off the Foursquare request, ask to get some data back from the API, kick off the Spotify request, ask to get some data back from the API. And then this will come back, could come back even a second later, and we're done. And then this guy comes back and maybe 2 seconds later, and we're done. So if you think about like why this is beneficial, it's because this is going to take us, 2 seconds, and then we wait 2 seconds, we call it, we wait for 2 seconds, and now we call this guy. So this gives me a total of 3 seconds. Whereas in this case, this is going to start, and then this maybe takes like less than 1/10 of a second to just make the request. And then while it's waiting, it's going to move on. And now this is going to take like 1/10 of a second too. All right? And now it waits to get back the response from the API. So far we've only taken up like 0.2 seconds. And then what happens? Well, the Foursquare, this comes back, like 2 seconds later. And maybe even before that, the Spotify comes back 1 second later. So, at 1.1 second, we get this guy back. And then at 2.1 second, or probably 2.1 second, or 2.0 even, we get this guy back. So the idea is, because what synchronous programming is doing is it's saying, hey, I have to wait until we've gotten the return value back from this function, from the kickoff to the Foursquare API. I have to wait until my Python process is going to continue on to the next function. Here, it kicks off the process and it doesn't wait. It goes straight to the next one. Okay? It goes straight to the next function. And because of that, we don't have to wait 2 seconds before we start this guy. Both of these guys have started making their request. Then, 2 seconds later, let's say Foursquare gets its answer back, and Spotify, 1 second after it makes the request, gets its answer back. So you've gotten a total of, right, like it's only taken you 2.1 seconds. Okay, you can really see this. Like if you imagine like you made 5 calls, these 5 calls, each of which that take 2 seconds, these with async, these 5 calls are happening right away, right? Kick off one, kick off the next one, kick off the next one, kick off the next one. Then 2 seconds later, we got this one back. Then I get this one back, right? Then I get this one back. Then I get this one back. Right? So the whole thing basically only takes about 2 seconds because this takes no time at all. It's the waiting around that takes a lot of time, and then we get back all the responses, right? So that's kind of the idea with asynchronous requests. With async, while we are waiting for a request, normally it's like an API request, an API response, we can move on to other tasks. And this officially is called like coroutines, I guess. With async, while we're waiting, we can do other things. Okay. So I give the analogy, like you can kind of, in terms of how this works, right? Let me close the whiteboard. I give the analogy of like, sorry, let me bring this over here, of like a waitress or a waiter, right, a server. With synchronous programming, it goes like one by one. I serve this person, then I serve the next person. Well, like you can imagine like Sweetgreen or going to like whatever, Chipotle. Like we have to wait, there's only one person helping us. We have to wait until the person like makes their decision. And then when that person is done making their decision, they tell us, their order, then we move on to the next person. If this guy waits for, like, if I'm at Chipotle and the guy is waiting for 3 minutes to decide, I'm not, as the server or the guy behind the counter, I'm not moving on to the next person until they have, give me their answer and I move down the line. And that's what we're normally doing with Foursquare, right? Or sorry, with synchronous programming. We are, calling one, and then we're not moving on until we've gotten our response back. It's literally, just like keep the analogy going. It's literally, right, we're making a request, and it's not until we get back the response, right, that we move on. Okay? Once we move to asynchronous programming, it's kind of more like, you're sitting down at a restaurant, and there's a server that's checking in on you. Okay? So officially what happens is we begin what's called, to move to asynchronous programming, you begin what's called an event loop. And then you have to say, essentially, you have to register these, they're called coroutines because it can happen asynchronously. But they're, register these functions. And I kind of think of it as like assigning tables to the server. Okay? And say, hey, you're responsible to check in on this table, and you're also responsible to check in on that table. Okay, so the first thing you can imagine the server does, it goes to this called Foursquare table, says, "Are you ready to order?" It's not going to wait, the 10 minutes for them to decide. If they say no, it can move on to the next table, right? And then check in, keep checking in until they're finally ready. And while they're thinking, it can move on to asking this task: "Are you ready to order? Are you ready to order? Are you ready to order? Are you ready to order?" So that's kind of like the steps that have to occur, right? You can think we have to, say, hey, now we're going to move into this like checking in type pattern, and I have to register all the functions that we need to check in on, right, in the event loop. And then the other thing that has to happen is, we have to kind of like, you can imagine that with the await part, this is where you're able to kind of like move on to another function. So if you think about what's going to happen here, step 1, down here, async io.run, we're now beginning the event loop. Here in this gather function, we're registering, these are your tables, right? This is what the event loop needs to check in on. Okay? The first step it's going to do is going to try to call the function, right? So it calls the function, it calls Foursquare. We get here to this await part. Once it hits await, this is the component where it is able to wait for a response, wait for the, wait for back for an event to occur. So it begins the sleep function, but this takes 2 seconds to be finished. So while it's waiting, because of this await function, it, one, can move on to other functions, and two, it cannot move on to this next line until this step has ended, right? So, and it's the same thing as taking an order, right? I'm not going to actually serve you until you've told me what you wanted, right? Until I get back a response. So it's the same thing here. It begins, checks in on the table, says, hey, can I take your order? Are you ready? The table is not ready. This await means that it gets to move on. Okay? It's asked the question, but it has not received back a response. Moves on to call Spotify. Same thing. We'll check in on call Spotify. Right? Call Spotify. Begin the call. Begin the function. Then once it gets to the await, while it's waiting, it is free to move on, right? And continue on with the event loop. All right, so that's, I hope, I'm never the best at explaining this, but I hope that makes sense, right? That's what each of these lines does, right? This is step one, we're beginning the event loop by calling this asyncio.run. So we're basically finished with our synchronous programming. Then step two, we register the coroutines, register the tables that you need to check in on, register the coroutines to check in on. Then in order, it will call them, right? So it'll call the Foursquare API. Go execute this function, we're good. Now I get to await. We've begun, right, this, but it has not gotten back a return value. So it's able to move on while it's waiting, and that's what it does, and moves and calls this guy, right? If this is registered. Then it goes down here, it waits 2 seconds, right? This thing's not ready yet, so it checks in on its other tables, checks in on the other coroutines, goes around. If this is ready, then it will get back the response and continue with the execution. Then it needs to make sure this is finished, right? So it checks in to see when this is ready, and then it will continue with executing it. All right, so you can see that. I like playing around with this to see it in code. So this is print begin the event loop. This is end the event loop. Right? When this is done. And now, or actually this is really begin it. This is register. Sorry, register functions. Done with all functions. It's calling all functions. And then this is my synchronous programming. All right, this is my normal programming. And now we're in the event loop, and now we're back to normal programming. Let's just like this. All right, so let's think about what's going to happen. This part here, right, is just my synchronous programming. So you can think of this as just go step by step by step. Then all of a sudden, we begin the event loop, right? We register the functions. We kick off, now we're checking in on them. We kick off on them, one by one. So this takes basically no time to run. It hits here, it's gonna have to wait. So immediately it's gonna call a Spotify call. Then it's gonna have to wait. It's gonna check in on this, but it's still waiting around for 2 seconds. So it's gonna say okay, we're not ready yet. Check in on this. Eventually this will be ready because it's only 1 second. And it'll call Spotify call finished. Right? Then it's going to keep checking on this guy until it's finally ready, and then it will call Foursquare call finished. Then this step is done. We should see done with calling all the functions. The event loop will be finished, and then we can go back to our synchronous step-by-step programming. All right, so let's just see that. Okay, so synchronous programming, normal programming, register the functions, right? Register, so it goes synchronous programming, normal programming. Register the functions. That's right here. Then the Foursquare, now that it's registered the functions, is checking in. So Foursquare call started. It has to wait, so it moves on. Spotify call started. It only waits 1 second as opposed to 2, so this thing finishes. It just keeps going around and around till it sees that this one is finally done, finishes it. Then finally, a second later, this is finished. Then once all the registered functions are done, it says done with calling all the functions. Then at this point, we're done with our event loop, so we're back to normal programming. All right. So that's it. The only other thing you have to kind of know is that there is a time.sleep function, but you have to use the asyncio.sleep function. Why is that? The time.io, right? Remember what we're kind of doing is I have to go back, save my stuff, is we're doing have an event loop. If you call time.sleep, or you have a thread basically that's running step by step, if you call time.sleep, even if you kind of have an event loop and then you say sleep, it's pausing the thread. Your event loop, like it's done going around checking on functions. Sleep actually sleeps the thread itself. Whereas asyncio does not, when you call asyncio.sleep, that is not sleeping the thread itself. So the thread is able to keep moving and check in on other functions. So while this thing is technically sleeping, but not really, we are, checking in on other functions. All right. So it's kind of like a technicality as why you have to use the asyncio.sleep, right? Because you don't want to actually sleep the thread. So I would use async if I'm building a stock trading bot and I need to pull different stock prices. Why am I doing this all the time? All at the same time. Yeah, so this is very, very useful when you're making many different API calls. Because if you think about it, right, if you have to wait 2 seconds or even 1 second for 100 or 1,000 different calls, if you have to wait 1 second, let's say, for 1,000 different calls, with synchronous programming, this is going to take about 1,000 seconds, right? With asynchronous programming, it's going to take about 1 second. Why? Because these 1,000 calls are going to happen immediately. And then we're going to wait a second, and then we're going to get back all 1,000 of them, basically one after the other. Okay? So you're saving, not a little bit of time. All right? This is a lot of time by doing something like this. The other thing, so I've been using the word thread, right? I talked about that in the reading. I don't know if you can see it in my Mac, if it talks about it. You'd have to look at, I guess, details about the chip. But as I say in the reading, if you try, people talk about multi-threading and let's get into that. That in most cases is not the optimal solution. And the reason why is because you only have so many threads on your computer. So you can say you have 3 CPUs and each of these have 4 cores, you get 12 processes and a thread occupies one of them. So that means you get to, you can do multi-threading. It's going to be harder to implement, and you're only going to get to occupy 12 at the same time through this. Okay, I want to use this, run processes literally in parallel. Here we're not running processes in parallel, right? While we're waiting, allowing this thread to do something else. That's asynchronous programming. It's one waiter, and we're just saying while we're waiting for the customer to give us back a response, we're letting my waiter move on to other tables, right? So it's a more efficient way, same thing as this. Is this similar to promises and callback concept in JavaScript? Yeah, it is similar. Yeah. It's been a long time since I've worked with JavaScript, and I think I understand it. But that is how I understand it. It's working the same way. What Narapati is asking. Yeah, Conwell, go ahead.
Yeah, if you could go to the code for the async algorithms, yeah. So what I understand from here is the line 11 and 17. I'm trying to understand async IO.C. This will be replaced with the actual API call like request.get or
Yes.
something like that.
Yes.
So why, when exactly this async IO thing will be used? My
It's
understanding is it not be used. The actual thing that matters is line 17.
Well, this is part of these are part of the. You're right. This is not you in a real life. You're not going to just sleep for no reason typically. So instead, this would be an API call. Async has its own mechanism also for making an API call that allows you to move on. So this line would be async's API call, which another reading gets into, which allows you to make the request and also move on to other things. And so that would you be using the async library. This actually, I think this might now be built into Python, but originally this was part of the async library. And then of course this starting the event loop and registering the functions. Right, these are also part of the async library. Mm-hmm. Cool. Try to explain this to yourself. You know. Also, I spent some time defining some terms. I do this because when you read about asynchronous programming, you come across these terms. So I just want to like demystify them. Right. A routine is just a Python program, like beginning to end. A subroutine is each function, and then a coroutine is these functions kind of get to operate concurrently, meaning like we are in the middle of calling them both at the same time, right? We're not waiting for one before starting the other. Cool. Um, I think that's it for now. Yeah, I'm pretty sure. Let's see if there's any other questions. How many event loops are there? One for the whole. No, you can have multiple event loops. I don't know if one event loop. My guess is you only get one per thread, though. That's my guess, but I'm not sure. Someone should check that. Um, but you can have multiple event loops if you want. The other thing you can do, of course, is like start your event loop back to normal programming, and then start another event loop, right? So you can do that too down here. Like let's say, of course, you want to call these functions multiple times. Let me just plug in my computer. Yeah, Kyle.
Yeah, you're starting to, maybe this is in the reading, but they say that Python is single threaded, but what this is doing, just to clarify, is orchestrating other computers through the API call, or is it actually using its own resources concurrently?
It's just using one thread. So
Mm-hmm.
like you can really think of it like multi-threaded would be if you think about like I would just keep going back to my server example. If you think about multi-threaded, it's like four different servers, waiters or waitresses operating at the same time. That's multi-threaded.
Yeah. Boom, 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 boom,
Right.
boom.
All of them handling different, we have four different tables. I have four different waiters, each of them handling a separate table at the same time. So that would be four times as fast, right? With this, it's one waiter, right? Who's, first they're just, waiting on this person individually. Wait till you finish ordering. Wait till okay, now that you're finally done ordering, I'll move on. But if you take 5 minutes, I'm waiting for you. You take 5 minutes, I'm waiting for you. Take 5 minutes. Here, let's imagine once we move to this new strategy, right, the event loop, you can take 5 minutes, but I'm just going to move on to the next thing. And because it's a computer, I can get to move on to that next program in, a millisecond. So it's asking 1,000 questions immediately, waiting 5 minutes for each of them to give back their answer, and then getting those 1,000 answers back, 5 minutes, like 5 minutes later. So the whole amount of time taken is basically 5 minutes and a little bit, right? The amount it takes to wait for one one coroutine is the amount it takes to wait for 1,000 of them effectively.
When does the multi-threaded become necessary?
I don't know. There's actually a good video I think I have on that. Um, it might,
You
I'll try
hear
to-
about it in like machine learning and training and stuff. And
Yeah,
that's why like GPUs rendering and
right. I think that would
but I
be
don't know.
that probably is a good reason. Julia was talking about that. If you think about like with ML, those just are long running processes. Like you're not waiting; it's crunching numbers the entire time, right? So you're not waiting around for some other computer to be giving you back some sort of answer. You're crunching numbers the entire time. So in that case, yeah, you can like cut your time in half or in quarters by using 4 different threads. But that's the extent, right? At a certain point, you then you need to buy more resources, etc. Right? You'll run out. That is a good use case that you gave for multi-threading.
But Python is intrinsically single-threaded because of this thing called the Global Interpreter Lock, the GIL,
The
GIL.
GIL.
Yeah, and it's kind of a weird, bad thing. And I think I've been reading that there's an upcoming version of Python that's actually going to get rid of that so that you could do multi-threaded programming in Python. That's what I've heard. But there is also the multi-processing module, which I think is like a built-in module, perhaps. And so you can, instead of doing multi-threaded programming, you could do where you create lightweight threads. You can do multi-processor programming, so you can have true parallelism that way. But processes are heavier, bigger things and more costly to get going.
There's a good. Let me find. If people are interested in looking at this, there is a really good talk on this. I'll put it in the Slack, and I'm happy to add it to the curriculum. And it goes through the differences and also like the trade-offs of them. But basically, the conclusion is kind of like for what we're talking about. You can just use one thread and not run out of resources by using async programming. So in those cases where you're just waiting around for something to finish, async is the way to go. For something where you're actually crunching numbers and you want to cut that time in half or in quarter, right, you can use multiple threads. Yeah, exactly. So Param's asking, are most languages multi-threaded by default? Most seem to allow it, but requires additional. That's kind of the way it works. That yes, I think almost all languages you can choose to use multiple threads, but it's not the standard way to implement. You're kind of specifically choosing to go that route and normally to import a library to do so. Cool. Let me find that. I'll find that video